Hi everyone, welcome to the channel. If you're new here, my name is Ryan and today I want to solve this FE exam thermodynamics problem for you. We're going to walk through the solution to this problem step by step and make sure that we really focus in on those fundamentals. Right? The fundamentals are going to be transferable between different problems, so it'll help you with the more broad subject of thermodynamics and not just this problem in particular. You can try this problem for yourself using the first link in the description below. It'll take you to this screen where you have the ability to flag questions, filter to see all the questions that we saw previously in our uh, FE exam playlist, and try this problem, which is the most important one. Once you try the problem, you can come back here and watch the solution for an in-depth step-by-step guidance. Okay, I hope you solved the problem. Let's get into the solution. Now you see the first thing I did was transfer it to a clean sheet of paper, because thermodynamics is one of those really input-heavy subjects, right? You're given a ton of information, so you need to sift through and see what's relevant and what's not. So let's go through slowly and read the problem. Firstly, it says a well-insulated rigid tank. I'm thinking of a tank here. Now I said it's well insulated, so that means that there's no heat transfer that crosses the boundary, the kind of inner wall of that tank. It says it's rigid, right? So that means that the volume change, the dV, is equal to 0. There's no change in the volume of that tank. It contains 5 kilograms of a saturated water mixture. So I'm thinking of a kind of TS diagram here where we have a saturation dome and we're somewhere within the saturation dome, right? Somewhere between the properties of a saturated liquid, which is on the left side of this dome, usually denoted by variable F or subscript F, and on the right of this dome, right, subscript G, which is saturated vapor. We're given the quality as state point 1, that's 30%. Quality at state point 1 is 0.3. Quality is just the percent of the mixture, which is vapor. So that's what we're given there, just in words. It says a resistor is supplied with a constant 110 volt and 20 amps. So I'm picturing a resistor here. And as that resistor is getting power supplied to it, it's getting some current and some voltage drop across that resistor. It's releasing heat into the system and it's going to vaporize whatever's inside. Over time, we're looking for how much time is that going to take. Okay, so overall, when I think of this system, I'm thinking there is some kind of energy input, right? We'll call that W. And there's no heat loss, right? Because we have an insulated system, so there's not going to be heat loss. And some of these terms I'm talking about should bring back a relevant equation, right? One of the most important equations in thermodynamics, the first law of thermodynamics. The heat transfer minus the work is the change in the energy of the system. Now, the change in the energy term for a closed system, which is what we have, there's no mass crossing the boundary. So that's how I know it's a closed system. That's the change in the internal energy plus the change in kinetic and potential energy. Thermodynamics is all about simplification. So that's the steps that we're going to walk through here. We always start with the first law of thermodynamics if you think it's relevant and slowly cross off these terms. First thing is that we're not given any speeds here, so there's not going to be any mention of a change in kinetic energy. No height changes mentioned, no potential energy change. There will be a change in internal energy when we think about, how's the energy of that water inside of the heated tank? How's that going to change? So there will be an internal energy change, and it looks like we are given the internal energy at state point 1 right here in this data. So we have the internal energy at state point 1. Let's first rewrite that internal energy term. We're given the specific internal energy, that's per unit mass, a kilojoule per kilogram. We would multiply that by the mass of the system. So mass times the change, the U2 minus U1 of the specific internal energy is what that delta U term is going to come down to. We know what the specific internal energy is at state point 1. We also know the mass that was given, equal to 5 kilograms. There is no heat transfer across the boundary. That's going to be 0. And I have a negative W term. Now, what is that work term that's being inputted? That's the power supplied to that resistor. The power supplied to that resistor, W dot, is equal to the voltage times the current. Because it's constant over time, that voltage isn't changing, as well as the current isn't changing, I can write that W dot as a W over time, or or energy per unit time. If I move that T over, I know what the energy is. The energy inputted into that resistor, that's just the voltage times the current times the time. So that's great. We brought into the problem one of the things that we're looking for, or the only thing that we're looking for, that time term. Now in thermodynamics, you have to be pretty careful about these signs. Work input is always a negative sign. Work output is a positive sign. Because we're inputting energy into the system, that's going to be a minus sign associated with that, and its magnitude is voltage times current times time. If we think about, is there any other kinds of work? There could possibly be boundary work, but when we think about it more clearly, the boundary work is equal to the integral of PdV. Now there's no change in volume, right? That dV is going to be equal to 0. That means this entire integral is 0. There's no boundary work for a rigid tank, right? The volume is not changed. So it's just the work done by that electrical resistor. Okay, so it looks like we have most of the terms here. We're going to solve for that time, which is just the mass of the system times U2 minus U1 divided by the voltage times the current. We know most of these things. The only thing we don't know is U2. If we think about what kind of properties do we know at state point 2, all we know is that at state point 2, the mixture will be fully vaporized. If we kind of turn that into a property, we know that the quality at state point 2 is equal to 1. The percent of the mixture which is vapor, if it's all vapor, that means that the quality is going to be 1. Now we need two independent intensive properties to be able to fully define the state. And we don't have that yet. We need one more property. And what's the property that we need? Usually when we have a closed system, when the mass isn't changing, the volume isn't changing, we think about what do volume and mass kind of characterize. What property is characterized by volume and mass? The volume per unit mass, since the volume is constant, the mass is constant, this term is going to be constant in the system. That's the specific volume. The specific volume is constant at state point 1, and it's equal to that at state point 2. It's equal to 0.2179. It's given in this box over here. So 0.2179, and it's equal to the specific volume at 2. And that's just the specific volume of a saturated vapor, right? We said we're fully vapor here. So we're on the right side of this dome here. You see that G I'm circling? So what we really need is the specific internal energy of a saturated vapor. Let's go in and see where exactly is the specific volume of a saturated vapor equal to 0.2179. And then we'll get a sense for what is the internal energy there. Okay, so I went straight to these thermodynamic tables, and what I know is that I'm looking for a specific volume of a saturated vapor equal to 0.2179. If I'm looking here, I'm seeing between the temperatures of 175, between the temperatures of 175 and 170, I have a specific volume, 0.2179. It's somewhere between those two values, right? So we could interpolate, but if I look, 0.2179 is very close to this value here, 0.2168. It's way closer to that value than it is to this upper value of 0.2428. So this column is the specific volume. I don't know if I showed that. That's this. So what we need to do is we would interpolate using that specific volume of a saturated vapor and the specific internal energy of a saturated vapor. But we don't need to do that because we're so close to this kind of lower bound here. We're just going to grab this 2580. That 2580 is just the specific internal energy of a saturated vapor, and it's pretty close to that. what we would get if we interpolated. So we're going to use that, save some time here. We know that the specific internal energy of a saturated vapor, that's approximately 2580 kilojoules per kilogram. If we plug in all of our values here into that time equation, we have the mass, that's 5 kilograms. Specific internal energy at state point 2, that's 2580, minus state point 1, we have 1135.47. We're going to take that value divided by the voltage, which was 110 volts, times the current, that's 20 amps. Let's make sure we work out some of those units. Remember, they wanted the time in minutes. So we're given the mass in kilograms, the specific energies in terms of kilojoules per kilogram, those are going to cross out. We know a voltage times a current is supposed to give us a power. That power is going to be measured in watts, and a watt is just a joule per second. So we have a kilojoule in the numerator, a joule in the denominator. Let's convert the kilojoule to joule. There's 1,000 joules in a kilojoule. So that's great. And then there are 60 seconds in a minute. Okay, so we end up with minutes. We have a conversion factor here of 10 to the third over 60. If you're enjoying the video thus far, please leave a like and subscribe. It really helps me out a lot and it's super encouraging. Let's get back into the video. Okay, so what we end up getting here is 54.7 minutes. Well, that's our solution. Let's go ahead and check that solution. All right, great. We got the right answer here. Let's view the explanation and quickly review what we did here. Now we had a rigid tank. We said that because it's rigid, the volume and mass is constant. The specific volume will also be constant. Because we knew that the specific volume was constant, we were able to get that second property that we need. The first one being that the quality at state point 2 was equal to 1, right? It was fully vapor. We fixed state point 2. We had state point 1, all the information was supplied. And then we used the first law of thermodynamics and the fact that the power was equal to the voltage times the current. Using the definition of power, right, that the fact that it's energy per unit time, we're able to bring time into the problem, and we solve for that time as well as all the properties that we needed, and we're able to find that the time required is around 54.7 minutes. You can see for that step where I skipped the interpolation, I have the interpolation steps here if you went ahead and did it and want to check your answer. And it didn't really make a difference in our answer at all. So if you made it to the end here, thank you for watching the video. Please like and subscribe for more content like this. I'll see you in the next video. Bye.